In this video, we're going to use calculus to explain how to better understand the mean and the median of a data set. So suppose that you have some data and you have n observations, x1 through xn. Well, the point of the mean and the median is to summarize the statistics. So recall that the mean is just the average. You add up all your data points and divide by n. So I'm assuming that all of these data points are just numbers. And the median is a number that's in the middle. So it's a number y such that for half of the numbers, so it would be that the number of xi's such that y is greater than xi is equal to the number of xi such that y is less than or equal to xi. Now this may be slightly different than the definition that you're used to. So for example, if you have an even number, so let's say that you have x1 is 3 and x2 is 6. Then typically a median would be defined to be the average of the two. So it would be 9 over 2 or 4.5. But in this definition, we can take, so a median of this collection of data is any number between 3 and 6. I guess if you don't want to include 3 or 6, you should make this a strict inequality. So maybe it's a little better to define the median using a strict inequality so that we don't include 3 or 6 as medians. Okay, so not including 3 or 6. There might be different definitions depending on what reference you use. So slightly different definitions of the median. But anyway, the idea is that these numbers give you one number that summarizes the data. So one question that you could ask is, well, usually it's a good idea to kind of pick both, to show both the mean and the median to get a better idea of the data. But what are the advantages and disadvantages of using the mean or the median? And calculus can help us answer that. So we're going to explain how calculus helps us understand the advantages, the pros and cons of using the mean versus the median. And that's what we're going to explain. So one way to measure how good, so the efficacy, I guess, so how good, I'm going to measure how good a statistic is, so in this case the mean or median, is to look at how much the statistic deviates from the data. That's not something with a precise meaning. That's just a vague kind of statement. But basically, you want to see how far off your number is from the actual data. So for instance, suppose that the mean, suppose that you have some number c. So suppose that c is just any constant. And you want to know how far away it is from the data. Well, one thing you could look at is you could take each of your data points and then subtract c, right? That would be the distance from the observation to the constant. To the constant c. So if x1, if your constant is 5 and your x1 was 6, then the difference would be 1. And if your c was 5 and your x1 was 4, then your difference would be -1. Okay. So one thing you can do is you can square the differences. Square all of the differences and then add up all the squares. So what you end up getting is x1 minus c squared plus x2 minus c squared plus all the way to xn minus c squared. Okay. And the idea, one idea is find the value of c that minimizes this sum. So it makes the sum as small as possible. Let's call this, so this is a function of c, let's call it f of c. Remember that in this case, your x1 or xn are constants that you're given. So for instance, suppose that your x1 was 3, x2 was 5, and x3 is 10. Suppose you have 3 data points. Then the function we're talking about is 3 minus c squared plus 5 minus c squared plus 10 minus c squared. Well, that's something that we can do with calculus. Right? We can do this using calculus. Because this function is differentiable. So we can just take the derivative and set it equal to 0. Well, what happens if you take the derivative? So I'm taking the derivative. So remember, x1 is a constant, right? So when I take the derivative, I'm taking the derivative with respect to c. So it's going to be 2 times x1 minus c, but then I have the chain rule because of the minus in front of the c, so it's going to be minus 2 times x1 minus c. And similarly, I'm just going to get minus 2 x2 minus c, and so on. So now I set this equal to 0, and when I divide by 2, okay, I'm going to get, divide by -2, I'm going to get x1 minus c plus x2 minus c plus ... plus xn minus c is equal to 0. Well, what is that? If I just combine the c's together, I just get x1 plus ... plus xn, right? And then how many c's do I have left? I have n of them, right? Because I have 1 c for each I from 1 to n. So I get minus nc equals 0. And now you just add nc to both sides and divide by n, and I get c equals x1 plus ... plus xn divided by n. Well, what is that? That is just the mean. And we can check that this in fact gives you a minimum, because if you take the second derivative, you are going to get I think I'm just going to get 2n when you take the derivative, and then that's positive. So since the second derivative is positive, you know that the function has a minimum when C is the mean. So the mean is the number that minimizes the sum of the squares of the differences. The mean minimizes the sum of the squares of the differences. That's kind of interesting. There's another way to measure the amount of deviation of a statistic from the data. So another way, instead of using the sum of the squares, is to look at, so you take the absolute value of x1 minus c and then add the absolute value of x2 minus c plus dot 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 plus the absolute value of xn minus c. So let's call this g of c to separate it from the f of c from before. So this is again a function of c. This time you're just looking at the differences and you're making them all positive, so you don't get -1 or anything, or 0, and then you're just adding up all those differences. And now the question is, which value of c minimizes this? So this is slightly more complicated than the discussion of the mean from before, because, well, what's different about this function? What's different about this function is that it's not differentiable at x1 through xn. So this function is not differentiable at x1 through xn. Right, because there's a sharp corner. Because of the absolute value. But we can still get an idea of what this function looks like. Well, before going on, I should maybe say that there's a bit of an argument to explain why this function isn't differentiable, because each of the individual absolute value functions just looks like an absolute value function, just shifted by a certain amount to the left or right. But then when you add them, the result is not going to look like an absolute value function. So g of c will not look like an absolute value function. But how can we show that this function is not differentiable at x1? Well, we know that at all these other points, at all these other functions, x2 minus c, that's the value of x2 minus c, all the way to xn minus c, this function is differentiable at x1. Right? So if g were differentiable at x1, okay, then you could subtract, you could do g of c minus this function that I underlined. And then since the difference of a differentiable function is differentiable, that would be differentiable. But the absolute value of x1 minus c is not differentiable at x1. And so that's the reason why. Okay. So to take the derivative, we have to be a bit careful. Well, what is, if we had something like the absolute value, let's call it h of x equals the absolute value of x1 minus c. Okay, let's call it h of c then. H of c is the absolute value of x1 minus c. We know that the derivative, so what this function looks like when you graph it, this is just absolute value of c minus x1. So if x1 is positive, then this function is just the absolute value shifted x1 units to the right. So it's going to look like this. So then this is a function of c. So the absolute, yeah, that's the function. That's your h of c. And so the derivative is going to be -1 if c is less than x1 and 1 if c is greater than x1. And it's not differentiable at x1. Okay? So let's look at, for instance, h of c is, let's just look at an example. The absolute value of 3 minus c plus the absolute value of 5 minus c. And think about what the derivative is going to be. So here's an example. Here's another example. Okay, if c, suppose that c is less than 3. Okay. If c is less than 3, then h is differentiable at c. And what is the derivative going to be? It's going to be, well, when you look at the absolute value of 3 minus c, the derivative at c is going to be -1, because we just saw that when c is less than 3, the derivative of this first term is -1. And for the same reason, the derivative of the second function, the absolute value of 5 minus c, is also -1. So the derivative when c is less than 3 is -2, because it's -1 plus -1. Similarly, if c is greater than 5, the derivative is going to be 1 plus 1, because the derivative of each term is 1 at c. So it's going to be 2 when c is greater than 5. Now if c is between 3 and 5, what's going to happen? What's going to happen is that the derivative of the first term is going to be 1, but the derivative of the second term is going to be -1. And 1 plus -1 is 0. So what this function looks like, h of c, so here's 3 and here's 5, it's going to have a slope of -2, so it's going to be something like this when you're less than 3, and then it's going to have a slope of 0 between 3 and 5, and then it's going to have a slope of 2 when c is greater than 5. That's what this function is going to look like. And we can think about what's going to happen in general. So in general, we have our h of c is, I call it g. So g of c is the absolute value of x1 minus c plus ... plus the absolute value of xn minus c. Okay. So if c is less than, so assume that x1 is less than x2 up to xn. Okay. So if c is less than x1, so c is less than all of your observations, then you're just going to have a derivative of -1 for each of them. So it's going to be -n. That's the slope. If c is between x1 and x2, then you're going to have 1 from the first term, but then -1 from all the other terms. So that's going to be -n. What is it going to be? It's, I think it's going to depend on if n is odd or even, right? Because if n is, so like if n is 2, then it's going to be 0, but if n is 3, it's 1. But I think it's just going to be n minus 2, or -n plus 2. And so on. Up to when c is greater than xn, it's just going to be n. Okay? So when is g prime of c, well, so what's going to happen is that your graph of g, okay, it's going to have a really negative slope when you are less than x1. And then between x1 and x2, it's still going to be negative, but less steep. And then between x2 and x3, okay, it depends on what your n is, but suppose that you had like a really large value of n, so then your slope would kind of get less negative until it had a slope of 0, and then it's gonna slope up again and get steeper and steeper like this. So this is an example of what g of c could look like. So at some point, it's going to have a slope of 0, unless you had something where it just went from negative to positive. So for instance, you could have something like this, and then a negative slope, and then a positive slope, and then like that. So you can have something like this. But either way, the minimum is going to occur. So the minimum is here. And in the first graph, the minimum occurs here. And there's lots of values where the minimum occurs. So here the slope is 0. Okay. So what is that number? Well, for each term in the slope, it's 1 if your c is bigger than that value, xi, or -1 if you're less than xi. So in order for the sum, so it's going to be a bunch of 1s and -1s, in order for that to be 0, this occurs when the number of xi's such that c is greater than xi is equal to the number of xi's such that c is less than xi. Well, what is that equal to? i.e., it's the median of x1 through xn. So what the median does is it minimizes this sum of the absolute values of the differences. Okay. So there are pros and cons to using this g of c or the f of c, which was the sum of the squares. So one difference is that if you have outliers, if the data has outliers, then what happens, how does the function f change? Then the function f changes a lot more than the function g, right? Because you're squaring the difference. So when you have a large deviation, so if you have an outlier, then that difference, when you square it, it's going to be really big, right? So that changes the mean a lot more. So the mean change, somehow the mean is, in some sense, more sensitive to outliers. It will change a lot more once you introduce an outlier than the median. That's probably something you learned when you learned about the mean and median, but now we see from the perspective of calculus why that is the case, right? Because the mean is minimizing the sum of the squares, and the median is minimizing the sum of the absolute values of the differences. And once you understand that that's what the mean and median are doing, then you can see how it will be more sensitive, how the mean is more affected by outliers than the median. Okay, so that's what I wanted to explain in this video. Thanks.